Dear students, let us continue our learning on the course Automata Theory and the Computability. So we are in the first session of the module 4. The topics covered under this session are algorithms and decision procedures for context-free languages. Myself, Dr. Suresh from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. First, the topic will be the decidable questions. So before that one, let us go back to the classes of languages what we have learned. So in the first class languages, in the first beginning classes, we learned the classes of languages called as the regular languages. So regular languages, we used to define the regular languages by using the notation of a finite automata. So either with the help of finite automata or with the help of regular expressions, we are able to find the solutions for the regular languages. That is, whether the string belongs to a set of language or not. That is, W belongs to the language or not. So this decision we have done for the regular languages. And to prove the languages are not regular, we use pumping lemma for proving the languages are not regular, which are built on the principle of a pigeonhole principle. Then next to that one, we went with the context-free languages. So for which we designed the two different types of notations we have used. They are, first will be your PDA we have learned, which stands for your push-down automata. Then we learned the context-free grammars. So the languages which were used in the grammars and the PDA will be your context-free languages. Context-free languages. So now in the context-free languages, we to prove a language is a context free, we can design a context free grammar or we can go for designing the push down automata. If you are able to design that one, then we can say that the language is a context free or else the language is not a context free. Then the obvious question, then the next question appears is whether the language is decidable. So when we say that word decidable, so decidable means if we design any program, so whenever we give some input, it should tell us whether it is an valid or invalid. The same scenario over here. So whenever I pass any string W, so it should the design automation, whether it is in PDA or it is in a grammar. It should tell us whether the string W belongs to that language or not. If that string W belongs to the language L, then we say that it is accepted or else it should be rejected. But the mission should halt on some end, some point. Fine. So such a class of languages will be your decidable thing. Right? That is, if you take up your exam writing as an example, after writing the exam, the university you should tell us whether the result is a pass or a fail. If it won't tell anything, then it is undecidable. So that is, a university should tell us the result. That is your decidable thing. That is, university result is a best example for your decidable question. So the decidable means what? Decidable doesn't mean that always accept. It should halt. It should halt and it should tell us whether the string belongs to that language or not. Right? So if I take the simple example, the strings ending with A, B, B, if I take one small example. Right? So and I designed an automation or a language for it, grammar for it. Let the grammar be yes derives A and the I will go to the capital A. Then next if I get the B, I will stay back in the same non-terminal B yes. Then next will be my A. So on the first A, I will go to the on the next B, I will go to the next state. Let it be capital B. If I get an A in the when I have a non-terminal A, if I get an A, then I will stay back at the A1. Then next on getting the next one that is B, on reaching the B. So on reaching the B means I seen one A, one B. I should get a one more B. Then I will go to the state C. I will go to the state C. Then next C derives epsilon. So this is my final state. This is my final state. So when I was in the B, if I get an A, if I get an A, then I will go to the state A. So that I will get the two B's next. Right? So now this is my grammar. So now if I have the string as A, B, B. If I have the string as A, B, B. First, what happens? I will start from the yes. So yes derives. What is that one? First is A. So means S derives A. Fine. Again, what is the next symbol? So now this is done. What is the next symbol? A. So now this A derives, what is that one on A? It will be A. That is A, and the A. Fine. So next, A derives. So what is the next symbol? B. It is A, B, and the B. Then next, B derives BC. Then A, B, B, C. C derives epsilon. So this cancels. So now we are able to derive our string. We are able to derive our string. So the given language, what is our language? ABB. So this belongs to that class of language. This belongs to that class of language. That is the membership. It is a problem. So what is that problem? We should be in a position to tell whether our given string belongs to that context-free language or not. Fine. So now, if it is the case, then we say that the string W is in the L or else it is not in the L. Fine. So now, given a context-free language L and a string W, there exists a decision procedure that answers that question. What is the decision question? W is in L or not. So now to have for the context-free languages, as I told earlier, there are two approaches are there for proving the context-free grammars. So one will be by using the context-free grammars, other will be by using the push-down automata. Right? So now let us take one by one. The first one. In the first one, let us use the grammar to decide whether the W is in L or not. Right? So this is the first alternative. We begin by considering the first alternative. We show a straightforward algorithm for deciding whether a string W is in language L or not. Using the fact about every derivation that is produced by a grammar is in the Chomsky normal form. So this Chomsky normal form we already learned in our previous classes. So we construct an algorithm that explores a finite number of derivation paths and finds one that derives a particular string W. That is, if we are able to derive our string W, then we say that there is a path. Then we say that there is a path or else we don't have the path. Simple. So now to decide, that is using the Chomsky normal form, that is decide the context-free language using the grammar. Fine. The input will be in a language L and the string W. if given in a PDA, then you construct your equivalent context-free grammar. Fine. So in the previous session, there was an algorithm for conversion of a PDA to grammar and grammar to PDA was there. Even though it is not in the VTU curriculum, but in the as a part of textbook, it is there. These two are equivalent. Fine. If PDA is given, you can convert to the grammar. If grammar is given, you can convert to the PDA. Fine. The next one. If W equal to epsilon, means the string itself is a epsilon, and if your grammar is nullable, nullable means what? Your starting symbol is with the starting symbol we are able to derive epsilon, then you can accept. Then you can accept, or else it will be get rejected. For the first case, if W equal to epsilon, W means what? A string. If a string is a epsilon, and if a start state of the grammar is nullable, then we say that the given string is accepted or else it is rejected. If it is not epsilon, fine. Then next we have to follow the next step. What is that one? Convert our grammar into the Chomsky normal form. So when we do the conversion, what happens? Obviously, the epsilon removal is an first step in your conversion of Chomsky normal form. Right? So now we have a grammar without the epsilon. Then if your grammar derives W in a majority of 2 into W minus 1 step, then we say that it is get accepted, or else we say that it is get rejected over there. Okay? The interesting factor to observe here is if W is not epsilon, then you have to convert the grammar into the CNF, Chomsky normal form. So which will produce the grammar, equivalent grammar, removing the epsilon production. Then next to that grammar, we can that grammar will derive our input string W in 2 into length of W minus 1 steps. Right? Then the next one, the second method. What is the second method? We use the PDA for deciding whether the W belongs to L or not. Right? As I told earlier, so in simple task, what we can do, we can convert our PDA to the context-free grammar. Then you can apply this one. Then you can apply. That's the simple step. Or we have one more option is also there. Fine. So let us explore them. So now it is also possible to solve the membership problem using the PDS, but it will take a two-step approach. So in the first step, we first show that for every context-free language, it is possible to build a PDA that accepts, that is the language minus epsilon that has no epsilon transitions. That is the PDA we have converted into the context-free grammar by using the algorithm which will convert the PDA to the context-free grammar. So once you have done the conversion, then next from the resultant grammar, you remove the epsilon production. That is, you can convert into a Chomsky normal form, CNF. Then if that CNF grammar, if that grammar derives your string W, then we say that it is accepted or else it will be get rejected. Fine? That is your first method. Fine? That is without the epsilon transitions. Then we show that every PDA has no epsilon transitions is guaranteed to halt. While not all PDAs will halt. So it is possible for every context-free grammar to craft a PDA that is guaranteed to halt on all the inputs and accepts all strings in W and rejects all strings that are not in the language L. Right? The method what we told above, fine. What is the first method over there? Given an PDA. So that is a PDA will be normally represented by the GNF, that is a Grebach normal form. That is convert your grammar to GNF, and from that G dash we can build the PDA over there. Second method, step 2. That is a M equal to P comma Q sigma B comma delta comma P comma that is a Q, that is a set of finite state. Right? So that to start our transitions, we can have the rule C derives a small c and S1, S2, S3 epsilon up till Sn. The transitions will be P comma C on epsilon. We will push these symbols. We will make the transitions to Q and S1 to Sn we are going to push to the stack. S1 to S1 we are going to push it to the stack over there. Right? The next, the second rule. For each rule which is of this format, what is that format? X derives C S2 up to Sn. If C belongs to sigma, then St to Sn are the elements of V minus sigma. So that is your gray batch normal form. So gray batch normal form will be like in this form. That is S derives. First should be in terminal, followed by any number of non-terminals like this A, B, C, and all. Right. So in this case, what happens if we have the production of this format? First case, that is a P comma C comma epsilon. So what we'll do on processing the, that is on processing your start symbol, we will go to the state Q and we push all the rest of the symbols. We push all the rest of the symbols will be pushed over here. Fine. Then next, at the beginning stage, we are pushing the start state, and next the rest of the productions we are going to push. Right? The next, for example, that is a halting behavior of the PDAs without epsilon transitions. Right? That is a PDA without epsilon transitions must halt. The PDAs without epsilon transitions must halt. Later, the theorem states that let M be a PDA which contains no transitions of the format Q1 epsilon S1 Q2 comma S2. Friends, we don't have the this format. That is, input should not be empty. That is, no epsilon transitions. Right? So consider the operation of M on input W belongs to sigma star. M must halt and either accept or reject W. Let n equal to length of the string W. We make three additional claims. What are the claims? Each individual computation of M must halt within n step. That is, it should be a finite one. The total number of computations pursued by M must be less than or equal to b power of n, where b is the maximum number of computing transitions from any state in M. The next, the total number of steps that will be executed by all computation of M is bounded by n into b power of n. Proof. Since each computation of M must consume one character of W. So each transition will take up one character of W, one character of W at each step, and M will halt when it runs out of the input. So each computation must halt within the n step. So if the string is of length n, and if the string is, we have not defined any transitions for epsilon, obviously what happens? For in each step, we are going to consume one input symbol. In each step, we are going to consume one input symbol of if the length of the string is n, after n steps, it should halt. It will halt. Then next, M may split into at most B branches at each step in a computation. The number of steps in a computation is less than or equal to n. So the total number of computations will be less than or equal to the b power of n. So if you have b branches, fine, with in each branch we have the n options, n characters. So what happens? First will be b power of n. That is the maximum value will be your b power of n. All your computation will be less than or equal to your b power of n. Right? Then the next one. Since the maximum number of computations is b power of n and the maximum length of each is n, the maximum number of steps that can be executed before all computation of m halt is n into b power of n. Fine. So next, the final algorithm for the deciding the CFL using the PDA. Fine. First, if L is specified as a PDA, use PDA to CFG to convert a grammar G such that both are equivalent. Yeah, that is language accepted by G is equal to the language accepted by M. If L is specified as a grammar G, simply use the G over there. If W equal to epsilon means it is nullable. It is a nullable, then you accept. If it is nullable, then you accept, otherwise you are going to reject it. If W is not epsilon, then there we have used a CNF. Here you are going to use the Gribach normal form. That is, first one should be in a lowercase, then the next will be the any number of uppercase letters. Then you can construct your PDA such that language will be the G dash with M as no epsilon transitions. Hence, because in the Gribach normal form, no epsilon transition won't be there. At least we need to have a single terminal. Then all paths of M are guaranteed to halt, because no epsilon is there means all will guaranteed to halt within a finite number of steps. So run the mission M on the W except if it accepts, or else you are going to reject it. Or else you are going to reject it. That is in the PDA. So that is it will be done with the help of the Gribach normal form. So there in the grammars we used the Chomsky normal form. Next, there. Decidability of emptiness and finiteness. The theorem statement is given a context-free language L, there exists a decision procedure that answers each of the following questions. What is that one? Given a context-free language L equal to null, not epsilon, it is null. Second one, given a context-free language L, L is infinite. Since we have proven that there exists a grammar that generates L, if and only if there exists a PDA, both are equivalent. That is, if we are able to solve a problem using the language, using the grammar, means the same thing can be solved with the help of the PDA. Right? So these questions will have the same answers whether we ask about the grammars or the PDS. Grammars or the PDS. Fine. So now let us go with the grammars. First one. Let G equal to V comma sigma comma R comma S. What V is a rule alphabet, sigma set of input symbols, R set of rules, S start symbol. Right? Is a context free grammar that generates L. If L of G equal to null, null means what? It is a non-unproductive one. We are not able to generate any terminal symbols. So for this one, we learned the algorithm of removing the unproductive symbols. Removing the unproductive symbols. So we learned the algorithm of removing the unproductive symbols. Means the productions which won't lead us to the final state. The productions which won't lead us to the final state. If we take one simple example. So S derives A or the B, and A derives small a, and B derives small b and the capital B. Fine. So if I take up the first one, so A, it is ending with a terminal. So yes, derives A. So this is ending in the terminal. Then if I take the second one, B, derives BB. Does the B will halt at some point of time? It will never halt. It's an infinite loop. Every time it will keep on repeating, getting the B. So how many times? It's an infinite time. It's an infinite time we will get that one. Does the string is of infinite length? No. And it should be a finite one. So now B is an unproductive symbol. So yes derives B. So this is an unproductive symbol. That is, we have to first remove all your unproductive productions before making your decision. Before making the decision about whether there is a language or not, we should go for first eliminating the unproductive symbols. The next step, if S is not present in the G dash, means that is not unproductive. If that condition fails, means it is a productive one. Then we can return the true or the false. Then we can return the true or the false. Fine. If it is not an unproductive one, then it is a productive one. What do you mean by productive one? On some conditions, they are going to halt and they are going to give us the result. They are going to halt and they are going to give us the result. That is, they are productive one. Right? The second case. Right? Second case will be, let grammar will be equal to v comma sigma comma r comma s. Be a context free grammar that generates L. We use an argument similar to that of your context free pumping lemma theorem. This pumping lemma theorem, actually it was there in the 13th chapter, but it is removed from your VTU syllabus now. Now it is not a part of your VTU syllabus, but for the sake of understanding, you can learn the pumping lemma over here. So what that pumping lemma over states? It states that given in string W, we are going to decompose the W into 5 components: U, V, X, Y, Z. Similar to that of your pumping lemma, what we use for your regular languages. What was that one? X, Y, Z. We have divided into only 3 components. And we have to prove that X, Y power of Q and the Z, where Q will take the value from 0 to N. Fine. So if that belongs to the your language, then it is said to be the regular, or else it is not regular. So we used it for proving that the given language is not regular. In the same way, for the grammars also, we have the pumping lemma, which will divide our input into 5 components. And if we are able to get this one, U, V power of Q, X, Y power of Q, W belongs to L, then we say that it is a decidable, or else we say that it is a undecidable problem. Fine. The next one. Right? So but assuming that the sigma is not empty, there is an infinite number of strings. Fortunately, it is necessary to try only a finite number of them. Suppose that the grammar G generates one string of length greater than b power of n plus 1 plus b power n, then t be the shortest such string. So by applying our pumping lemma, we can define that the given context free language is finite or infinite, that we can decide. Right? So that is, first we have to lexicographically enumerate all the strings. What do you mean by lexicographically enumerating? First the strings of length 0, then the strings of length 1, let it be A and the B, then the strings of length 2, AB, AA, then BB and the BA. We are going to get the 4 combinations over there. Then the strings of length 3. If we keep on repeating, at some point of time we are able to get the strings of length B power n. Fine. The length of the strings greater than the B power of n. So what it will be? Then it will be less than or equal to your B power of n plus 1 plus B power of. B power n plus 1 is next combination. B power n is your previous combination. So that is totaling that one. That is the strings from starting from 0 till your B power of n plus 1. If it is the case, then we say that it is an infinite one. That is the CFL is infinite one. If for any such string W, decide CFL will returns true, then it is said to be infinite, or else it is not infinite, means it is a finite string over there. Right? So this is here we are using the pumping lemma for the proving purpose of whether the string is a finite or infinite one. Right? Then the next topic. So when we have decidable one, in the same way we have the undecidable problems also over there. There are some undecidable questions for which we are not able to come to a final conclusion of whether the given language is decidable or not. First class of language. That is, if L equal to sigma star. Second class of language. Complement of L. Suppose I have a production as A derives AA, B, C. Then the reverse of it. Complement of the L. The next one. Given a L is a regular. The next one. Two context-free languages, L1 and L2, whether they are equal. The next one. L1 is a subset of L2. The next one. L1 intersection L2. It is undecidable one. Let us take a simple example. I have a first class of languages as A power n, B power n, C power m. Intersection with A power n, B power A power m, B power n, C power n. What is the intersection of this one? A power n, B power n, C power n. So this is not a context-free language. A power n, B power n, C power n is not a context-free language. We are not able to write in grammar for it. You can try it out. Right? So such class of languages, even they are undecidable. Right? So these two are regular, these two are context free. For them, we can write the grammars. But for this one, we can't write the grammar. We can't write the grammar. So such a class of languages. The next one, given a context free language, L, if it is an ambiguous grammar. Right? So inherent ambiguity is there. The next one, if the grammar is ambiguous one. So in all these cases, we are not able to decide. These class of languages, we call them as the undecidable questions. These class of languages, we call them as the undecidable questions. Okay. This will be regarding the first topic of the module 4, which focused on the decidable algorithms and the decidable problems in the CFL. Okay. So in the next session, we start with the Turing machines. The references which are used for these presentations are from the textbook Alan Rich, Automata, Computability and Complexity, first edition, Pearson Education 2012-13. Thank you.